Okay, we're going to learn two new tests today in section 9.5a. The first one we're going to do is called the integral test. First of all, we have to let our general nth term, a sub n, be a sequence of positive terms. So let's suppose a sub n is going to equal our function. So where f is a continuous, positive, and decreasing function. Okay, but here's a little catch. It needs to be a decreasing function of x for every x greater than or equal to n, where n is some positive integer. So like if in the beginning you have a function and it maybe increases, decreases, increases a little bit more, but eventually, like in this graph right here, at some point n, it's always going to be decreasing, then that's okay. So if all of these things are true, then what our test says is that our series from n equals to big N, our series and our integral will both converge or they will both diverge. Our series is going to behave just like the integral. So let's try an example. I want to prove the convergence or divergence of this series, 1 over n squared. I'm going to consider a sub n, which is my 1 over n squared, and I'm going to let that be my function, f of n. Okay, now again, why are these different? Because in reality, this series is really only 1 plus 1/4 plus 1/9 plus 1/16. So in terms of a graph, if we assume this to be 1, and we go 1, 2, 3, and so on, it's going to be points here. 1, 1, 2, 1/2, 3, 1/3, 4, 1/16, and so on. Okay, they're just dots. It's not continuous. So we are going to liken it to some function where this is going to be f of n. Okay, it'll be the whole thing filled in, no spaces in between. First thing we're going to check is that it is continuous, and I know that to be true because 1 over n squared exists everywhere from 1 to infinity. I know it's always positive, and then I also know that it is decreasing because as I've written out my first 4 terms, they're getting smaller and smaller. So I've checked these 3 things. They do work, so now I'm going to integrate. I'm going to go ahead and write x squared instead of n. So it's going to be x squared dx. So I have to write it limit as b approaches infinity, and I'm going to go ahead and integrate 1 over x squared. That's negative 1 over x. And we're going to evaluate from 1 to b. So that's the limit as b approaches infinity of negative 1 over b plus 1. And as b goes to infinity, that fraction goes to 0. So this limit equals to 1. Now, does that mean the sum of the series equals to 1? No. It means that the area under the curve of that function equals to 1 because the integral converges. By the integral test, we know that our series converges also. Let's take a look at another series. From n equals 1 to infinity of n over e to the n squared. Let our n over e to the n squared be our f of n. I want to check to see that it is continuous. So does this value exist everywhere from 1 to infinity? Yes. Are all the terms positive? And that's a yes. Now the next thing, are all the terms decreasing? So that would be like 1 over e to the 1. And then you would have 2 over e to the 4th. Then we have 3 over e to the 9th, and so on. Yes, the denominator is getting bigger, so it is decreasing. So we're going to go ahead and use the integral test. So that means we are going to calculate the integral from 1 to infinity of x over e to the x squared dx. But I'm first going to write a limit as b approaches to infinity, okay, and I'm going to write x e to the negative x squared instead. So this is actually going to be negative 1/2 e to the negative x squared. So after I plug my numbers in, I have negative 1/2 e to the negative b squared plus 1/2 e to the negative 1 power. Now b is going to infinity. It's a negative exponent, so that means this whole thing is going to go to 0. So our integral converges to 1 over e. So because the integral converges, we can say by the integral test, the series n over e to the n squared converges also. So now we're going to do an extension of the integral test. The p-series test is really just a subset of the integral test. So in this case, if you happen to have a series that looks like this, where it's 1 over n to the p power, if p is greater than 1, the series converges. If p is less than or equal to 1, the series diverges. This stuff right here, we proved this in our Chapter 8 note. Did you guys get a chance to go back and look at example 1? I want to talk about that for example 3, just in case you didn't. 1 over n squared. So you see how that fits the p-series test? We just say that it's a p-series, identify what p equals to. P equals to 2, which is greater than 1. Therefore, the series converges. Now, what if we had a series and it looked like this, 1 over n plus 4. This is really 1 over 5 plus 1 over 6 plus 1 over 7 plus 1 over 8, and so on. This is the exact same thing as saying I have 1 over n, but where am I going to start my series? I'll start my lower limit at 5. Now think about it. If you have a series and it's 1 over n, and it starts at 1. This is p equals to 1, therefore it diverges. Now if you have a series that's going to diverge, and I take away the first 4 terms, do you think it's still going to diverge? Yes, because it's getting larger and larger, going to infinity. You can take out even 100 terms, the first 100 terms. It's still going to diverge, no matter what. So for this type of thing, we can be a little bit creative. We can adjust our starting point. Then we can say that it's a p-series. P equals to 1, therefore it diverges. How about n to the negative 1/3 power? What's p? This is really 1 over n to the 1/3 power. So what we say here is that we have a p-series. P equals to 1/3, which is less than or equal to 1. Therefore the series diverges. Okay, the very last thing I want to talk about today is something called harmonic series. A harmonic series is a specific name for a type of series, and what it is a p-series with p equals to 1. This is going to be 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, and so on. If you ever see this series show up anywhere, you can go ahead and say that it's a harmonic series and that it diverges. So we're going to do one last one. 2 times n over n to the 5/3 power. We're going to rewrite this. I can simplify and combine my n over n to the 5/3. And this 2, it's not going to affect anything in my sum, so I'm going to go ahead and pull that out. So I'm going to have 2 times the sum of n over n to the 5/3 power. So we can simplify that and give ourselves 1 over n to the 2/3. This is a p-series with p equals to 2/3, which is less than 1, therefore it diverges. Okay, so look for the integral test, the p-series test, nth term test, ratio test, and geometric series for this homework.